Today we're going to cover a couple of reactions. We're going to cover epoxidation, because it's still a type of oxidation reaction which we've been doing. And we're also going to cover hydrogenation. Right, so those two reactions. And then there's a handout, well, there's a part of this handout that we're going to start working on. To kind of get some practice doing these reactions. All right, so let's look at real quick a generic version or generic overview of epoxidation. Then we're going to go up and do the epoxidation problem that's on the handout that we're working on Friday. And then we're going to, for hydrogenation, we're going to look at the other handout that we're going to start working on today. All right. So what is an epoxide? Right. So epoxidation is conversion of an alkene into a cyclic ether. Cyclic three-membered ether. All right, what's an ether? Somebody remind me from the functional groups. When we went through the functional groups, what's an ether? Anybody remember? It's a very common functional group.
Is that the one that has the O in the middle and it's attached to a carbon on each side?
Yes. Who was that? Kayla?
Kayla.
Yeah, you're right. Thank you. That's exactly right. So an ether looks like this, right? Where you have O, let's just draw a simple one, CH3 on this side, and then a CH3 on that side, right? That's an example of an ether. So an epoxide is an ether, but it's not open, it's cyclic, right? So instead of being looking like this, the epoxide actually it's the same functional group. You still have a bonded carbon on each side, but it's a cyclic three-membered ring. So here it'd be like a CH2, and then here would be a CH2, right? So this is what we call an epoxide, right? It's a fairly simple reaction, and there's more than one way to do it, right? There's two different sets of reagents to make epoxides. One is, I'm gonna write this right here. I'm gonna say synthesize two ways. Right, so you have two ways you can synthesize epoxides. One way is to use hydrogen peroxide and sodium hydroxide. So you can take an alkene like this, and then the reagents are H2, O2, and then NaOH, right? Hydrogen peroxide, sodium hydroxide. When you do that, what you get is an epoxide, right? So let me zoom in on that so I can fix it. Right, you get an epoxide where these are your two carbons that were in the alkene. All right, and then you get water and sodium hydroxide on the other side as well. Right, there's another way you can do this. And you can, and this method would be for electron rich alkenes. So I'm going to just stick a CH3 on here, right? You can do it using what's called Mcpba. I'm going to tell you what that is in a second. So hydrogen peroxide and sodium hydroxide is one way. Mcpba is another way. This is for electron rich. Right, and the way you make alkenes electron rich is you put carbons around it. So you substitute them more, right? So it'd be mono substituted, di substituted, tri substituted, so on and so forth. You should be familiar with that terminology by now, all right? So with the alkene here, my epoxide is going to look like this. Let me fix this over here too. And I'm going to show you what the structure of McPba is. So don't panic about that. So it's that plus benzoic acid. Right. All right. So let me add another page right here right quick so I can show you how both of these work. And we're going to go back up to the example up top and make sure I got the date on here. So when you look at this, you won't be scrambling, trying to figure out what's what. I got 1026. All right. Let me stick a page in here. All right. So I'm going to do the first, the hydrogen peroxide first. So again, these epoxidations are oxidation reactions, right? What does that term mean? Anybody remember? I gave you two terms the other day, oxidation and reduction. What does oxidation mean? Not in terms of general chemistry, right? Because that's loss of electrons, and then reduction is gain of electrons. But what about for organic? What does it mean? If I oxidize something, what am I doing to it?
Aren't you trying to get more oxygens?
Yeah, I'm oxidizing, right? So I'm adding oxygen. I'm increasing the number of bonds to oxygen. And then by the same token, for reduction, reducing the number of bonds to oxygen. There's another part to that definition that I'm gonna give you today. So you increase bonds to oxygen or decrease the bonds to hydrogen.
So not necessarily like adding more oxygen, it's just adding more bonds to oxygen.
Yeah, but sometimes in some cases you are actually adding, like this is an example where you're actually adding oxygen, right? Because you don't have an oxygen to begin with, and then you have one in the product. But sometimes it could be increasing the number of bonds to oxygen too, right? So it's like, which adding oxygen is the same thing, but sometimes you might have an oxygen present that you can convert into another functional group. Like if you have an alcohol and you turn it into aldehyde, that's an example of oxidation because you made more bonds to oxygen. Right, so for oxidation, it's increasing the bonds to oxygen or decreasing the number of bonds to hydrogen. And then for reduction, it's the opposite. Reduction, you decrease the number of bonds to oxygen and increase the number of bonds to hydrogen. I'm just going to copy this and paste it on the sheet. Yeah, so reduction is just the opposite. Decrease the number of bonds to oxygen or increase the number of bonds to hydrogen. So epoxidation is a type of oxidation reaction, right? I'm gonna increase the number of bonds between carbon and oxygen, right? So if I do, let me see, I got enough room. If I take the hydrogen peroxide, let's look at that one, that mechanism. Right, so the first step, so this is actually a very straightforward mechanism. First step is to deprotonate or do a proton transfer on your peroxide. Right, so this is my hydroxide from sodium hydroxide. I'm going to pluck off the proton here. And then I'm going to give this is just a proton transfer. We've done this already, right? So then what I end up with is the peroxide anion that looks like this, plus water. And then the sodium from sodium hydroxide ends up with that anion. All right, any questions about that? So this is nothing new. This is all, again, all these mechanisms, all these reactions. If you understand nucleophiles and electrophiles and acids and bases and proton transfer or nucleophilic addition, if you understand that part, this is not new. This is just application. All right, so the first step is to make that, we're gonna call it the peroxide, right? Anion. And then in the next step, that anion is going to attack your alkene. I got to zoom in on that so I can make sure I have enough room to fit it. All right, so here's my alkene, and then here's my anion right here. Right? What do you think is going to happen if I want to add that oxygen? If I want to make a bond to both carbons in the alkene, I'll go ahead and write those carbons in too. Right? So let's say the oxygen attacks one carbon. Say it attacks that one. What do you think is going to happen to the pi bond?
Gonna break.
Don't all answer at once now. We won't want it to be too loud in here. If I attack that carbon and that alkene, can that pi bond stay intact?
No.
It can't,
No.
right? So when the oxygen attacks that carbon, the pi bond attacks the oxygen. So that's how you get the bonds on each side. You get a bond to the, let's label them. You get a bond to this carbon between carbon and oxygen. And then on the other side, the other carbon is going to use those electrons in the pi bond to attack oxygen. What else do I need to do? There's one other thing that I'm missing. Can the OO bond stay like it is?
Is there going to be a plus charge on the O?
No, there's no plus charge. This is all concerted. That's a great question. If it was stepwise and it had an intermediate, then yes, you would put a plus charge on oxygen. But the fact that it's all concerted, all of these bond making and bond breaking processes are happening simultaneously. So I need to break that, the OO bond. Are you following? Y'all following that?
Yes.
Right, so once I break it, then I get my product. I get my epoxide here, right? And I'm gonna put my CH2s back in. That's so sloppy. So I get my epoxide plus OH minus. And then of course the sodium from the previous, sorry about that. The sodium from the previous step is still around, so I'm just gonna stick that back onto that OH minus. Any questions about that mechanism? So you get the epoxide plus sodium hydroxide, and then of course we made water in the previous step, so I'm gonna put that back down here, plus water. So the first step is to basically make the peroxide a better nucleophile, and you do that by doing proton transfer. And then the second step, the peroxyanion attacks the alkene, and that's how you get your ether, your cyclic ether. All right, any questions? So you got to have a working knowledge of your nucleophiles and electrophiles and sources and sinks. That's why we spend so much time on that, to kind of make sure that when you start seeing stuff like this, it's not just Greek to you. You know what I mean? So let's look at the McPba mechanism, and then we're gonna move on to something else. So the hydrogenation, we're gonna cover that too. Come on now, stupid computer. Sorry, you didn't hear me say that. All right, so the McPba mechanism. Okay, never mind. All right, it's a little different because there's no base or anything like that. So here's my alkene. Well, first let me show you what McPba is. So McPba is here. It's that's the structure of McPba, right? It's metachloro perbenzoic acid. The per is in there because of the extra. I'm gonna show you the difference. Right, so the per is in there because you got an extra oxygen. So a peroxide is it's a hydroxide has an extra oxygen. So the peroxide is indicative of the fact that you have another oxygen present. So benzoic acid looks like this. well, metachlorobenzoic acid looks like this. You see the difference? Here, you have an extra oxygen between the O and the H here, right? And you don't have that in benzoic acid. So benzoic acid is not a per acid, but McPba is. Right, so that's why it's called per benzoic acid, because it's got that extra oxygen in there. All right, we're okay with that? All right, so there's no activation step. There's no base, there's nothing. This thing, when you put this per acid in the presence of an alkene, they just hook up. So let me show you how it works. And then we're gonna go up to the question up top and see if we can answer it. This pen makes me sick sometimes on Mondays. All right, so let's look at it. So here's my alkene. All right, and again, this is all concerted. There are no intermediates. It's all concerted, all happening at the same time. So here's my alkene. I'm gonna change the color of that. So I have an alkene here. And again, keep in mind, all I care about is what happens to the alkene. Everything that we've covered up to this point has been reactions of alkenes, right? So I don't care about that CH3. I don't care about if my alkene has other functional groups present. All I care about is what's happening to the alkene, right? So the perbenzoic acid comes in here. Let me see if I can steal this. I'll try to cheat so I don't have to redraw it. Let me see. All right. Let me move this down some more. And then I'm gonna show you exactly what happens here. I got plenty of room. All right. I need to get a user different. All right. So what actually happens here, so you get some, this is actually activated. I'm gonna show you right quick by hydrogen bonding. So this oxygen right here, the one in the carbonyl, is going to hydrogen bond with the hydrogen here. And that's where your activation is going to come from. All right, so now my alkene again is going to attack. Let me put some long pairs in here too. My alkene is going to attack this oxygen. Right? So I'm going to take the OH bond, I'm going to use those to attack the alkene. And then the alkene is going to attack oxygen. That's where my ether is going to come from. Now the rest of the arrows in the mechanism are here. I'm going to break the OO bond and put that here. And then the CO pi bond, I'm going to use those electrons to pick up hydrogen, right? Any questions about that? So I'm using the OH electrons to attack the pi bond. Once I do that, keep in mind, once I use those electrons between O and H, that bond no longer exists between O and H. Now it's going to be a bond between this carbon right here on the alkene and oxygen, right? And by the same token, once I use that pi bond is no longer going to exist in the product. It's going to be used to make a CO bond between this carbon. Let me see, this carbon right here and oxygen. All right. Any questions about that? So what I get out from that is this, right? I'm going to get an epoxide that looks like this. I'm going to write the carbons in. Still a hydrogen here. Come on, pencil. Here's my oxygen from the Mcpba. So you can see again, this is an oxidation. Boom, so that's my epoxide. Plus benzoic acid. So that's the product from that arrow shuffling is going to look like, well, not benzoic acid, metachlorobenzoic acid. I think I said benzoic acid up top too. But it's metachloro because of the chlorine. All right, remember this is all concerted. Right, no intermediates. And it's activated by hydrogen bonding. All right, questions. Ask questions. So we've seen the mechanism for both the hydrogen peroxide reaction as well as the metachlorobenzoic acid reaction. All right, so let's go back up to here. And let's see if we can answer this question. Right, what did we get from, it says choose the product from the following arrow pushing mechanism. All right, so look at the arrows that we start with. Right, what does this arrow indicate? Let's see if we can do that. What is this arrow telling me right here? What is that arrow saying?
The bond between oxygen and hydrogen is breaking.
Yes, and I'm using those electrons to make another bond, right? In this case, it's going to be between the carbon and the oxygen, right? Why not the hydrogen? Let me see how you're thinking. Why not the hydrogen and the oxygen? Which atom, if you have an OH bond and you break it heterolytically, which atom is going to get the electrons?
Oxygen.
Oxygen, right? So that's how you know which atom is going to make that bond when you take that pair of electrons from between O and H. What is this arrow telling me?
That the double bond is breaking
Mm-hmm.
and the bond between carbon and oxygen is forming.
So I'm using the electrons in the pi bond to make a bond between carbon and oxygen. Good. So on the right side, I'm using those electrons to make a CO bond. And then here, I'm using the same thing, electrons, and that pi bond will make a CO bond. All right. So all the rest of it, what is this arrow telling me right here? What's that arrow saying?
O and O bond is breaking.
Breaking the OO bond. And what am I doing in the same process? Look where the arrow stops. Doesn't it stop here? Between these two atoms. So that means I'm breaking that OO bond and I'm making a pi bond between carbon and oxygen. Are y'all following that? Anybody not see that? All right, and then right here, what am I doing with that arrow?
Creating a hydrogen bond.
I'm making an OH bond. I'm breaking the pi bond. All of these bond breaking processes, how would you classify them? Homo or hetero?
Hetero.
Hetero, right? Heterolytic. All the bond making processes will be heterogenic, right? If you look at the arrowheads, I'm not using single-headed arrows. So these are all polar mechanisms and concerted mechanisms. What does concerted mean? Anybody?
Like all at once.
Yeah, it's all your steps happening simultaneously in a given mechanism. All right, so everything is happening all at once. There's no intermediates. So what's the product from that mechanism that's shown over there? What would you get? What can you rule out?
C.
C, good. Rule that out. What else can you rule out?
Is it B since no cyclic?
Yeah, B.
What's one?
Yeah, we can rule out B too. That's exactly right. So now you got to choose between A and D. Which one is it, do you think? Why wouldn't it be A? Let's narrow it down like that. Why wouldn't it be A?
I feel like you said last time there's not supposed to be an intermediate.
Yeah, no, there's no proton on the oxygen. If you look at the mechanism, where's that hydrogen going? Which oxygen? Right, you got a choice between it going here or here. But if you follow the arrows, which one of those oxygens is picking up the proton?
The top one.
The top one, right? So the epoxide can't have a proton on oxygen because in the mechanism, the OH bond gets broken. Isn't that what this arrow, we said this arrow right here indicated? That we're breaking the OH bond. So it can't be a hydrogen on oxygen in the product. So the answer has to be D. Right? This is, and again, if you want to just go back and think about it in simple terms, it's Mcpba reacting with an alkene. That's always going to give you an epoxide.
I have a question.
Go ahead.
I forgot. What does the dotted line between the O and the H mean again?
It's a hydrogen bond.
Okay, so that's just straight hydrogen bond. Okay.
Do you remember that when we talked about intermolecular forces?
I just wanted to make sure.
Yeah, it's a hydrogen bond. So that's what's activating the reaction. That carbonyl oxygen hydrogen bonding with the OH proton, that's what makes the OH bond susceptible to be broken. And it also activates the breaking of the OO bond. Because low key, the oxygen bond is very weak anyway, because both oxygens have a bunch of electrons around them. So they're repelling each other from the jump. So that's a really weak bond. So it's easy to break that bond in relative terms compared to other bonds.
Okay, thank you.
Good question. All right, let's go down to this handout, and I want to start working through some of these reactions. I don't want to bombard you with just mechanisms on top of mechanisms. So let's see what we can do here. All of these reactions we know, except this one, and we're going to look at that one by the time we close out. Right, this is the only one that we don't know. But it's one of the reactions that we're going to cover today, the hydrogenation. All right, so let's look at where y'all want to start on the wheel. We can start at 3 o'clock. We can start at 4 o'clock, 6 o'clock, 7 o'clock, or 9 o'clock. We already did 9 o'clock because that was the osmolation. We talked about that Friday. Where you want to start? Let's just do the ones we already know first. We're going to start at right here. What type of reaction is that? That's the first question. If you look at the reagents, you should be able to identify the reagents and call the reaction out immediately. So what type of reaction is that?
Oxymercuration.
Speak up. You're right.
Oxymercuration.
Oxymercuration. Good. I'm gonna write it down, and then we're gonna predict the products. What does oxymercuration do?
Adds mercury and water across the double bond.
Okay, but what's the final product? You're right about the water, but what do you get from as a result of oxymercuration? It's a way to turn alkenes into what?
Alcohol.
Good. Alkenes and alcohol. Is it Markovnikov or is it anti-Markovnikov?
Markovnikov.
Good. What does that mean? Where's the OH going to end up? That's what the Markovnikov tells you, the regiochemistry.
On the most substituted carbon.
Good. On the most substituted carbon. Is the double bond still going to be present in the product?
No.
No. It gets used up. So if you see these reagents, and this is your start material right here, what are you doing to that start material? You're going to turn it into an alcohol. You're going to add H to one side and OH to the other side. Which side is the OH going on here? We only got two choices. Because again, don't get bogged down with the CH3 or the rest of the ring. All we care about are these two carbons in this double bond. That's it. So where's the OH going to go and where is the H going to go?
OH is going to go on the left.
So on the same carbon with the CH3?
Yes.
Yeah. All right, good. I'm gonna put some stereochemistry in here too, because I want to make a point about this reaction, all these reactions. Right, so I'm gonna move the CH3. I'm gonna put that on the dash. Sloppy. Come on, Russell, get your life right. I'll tell you what, I'm gonna put the OH like that. And I'm gonna put the CH3 on the dash, right? And then the H is over here, but I don't really have to show that. Right, but the H and the OH that I added are always going to add to the same side, right? It's sand addition of water. Just like with the hydroboration, always going to add to the same side. All right. Any questions about that one? That's what we get, right? We get an alcohol with the OH on the most substituted carbon because of the regiochemistry, right? We said we use this MEM, mercury is Markovnikov, right? Is that right?
Yes.
All right, let's go to the next one, right here. What is that reaction? What's going to happen? How is it going to happen? We're not going through no mechanism. We're just predicting the products. If you see bromine and water, what reaction is that?
It's gonna be halogen.
Who was that?
Brittany.
Brittany Melton.
Don't be saying my government name like that.
I'm calling your whole government name because you are absolutely right. No, that was a glee, joy. That was joy coming out.
Okay.
Yeah, it wasn't bad. It was good. That's a halogen formation. Okay, great. What does that give me? Like, what product do I get when I take an alkene and react it under halogen conditions? What's the product?
You're gonna get but the alcohol and the BR on opposite sides, so it's gonna be trans.
Look at God. Look at God. Just giving you all that wisdom. Somebody been studying. That's a good thing. All right. So you're gonna get, where's the alcohol gonna end up? Which carbon? That's another important part about this, excuse me, about this mechanism. What do you think?
I just know it's gonna end up like on top.
Okay. Is it gonna add to the most substituted carbon or the least?
The most.
Most. Good. Who was that?
Kayla.
Kayla. Come on with it. Make it a competition. So the alcohol is going to end up here. If I can write, I need to go back to kindergarten. That's going to push the methyl back. Russell, come on, man. So the CH3 is going to be here. Where's the bromine going to be? Relative to the OH. Is it going to be same side, opposite side? I heard you say it.
Opposite side.
Opposite side. Right? You always get trans addition. So the bromine is going to be right there. Right? And that is my halogen formation. Right? That's good. All right, let's do the other reaction over here at 8 o'clock. Let me move this. Uh-oh. Shrink it down. All right. What kind of reaction is that?
With the HCl one?
Mm-hmm. That's what we're doing now. What reaction is that?
Electrophilic addition?
Of HX?
Yes.
Come on now. Who is that?
Kayla.
With some terms. God dog. Man, y'all gonna make me shout today. I ain't even shout at church yesterday. You're right. It's electrophilic addition. What happens in that reaction?
You'll get an alkyl halide. So basically, the chlorine will go on the most substituted carbon.
So we're going to get an alkyl halide. And
yes.
You said the chlorine is going where now?
On the most substituted carbon.
Most substituted carbon. Very good. You're absolutely right. So the product is going to look like this, right? Excuse me. Here, boom. I'm gonna keep the stereochemistry consistent here too. So CH3, and then the chlorine is gonna be here, like that. Is that right? And then my H, I'll put it right here. Yes or no? I added H and I added Cl across that double bond. Is that right? Or an electrophilic addition.
Looks right to me.
Mm-hmm. And what type of regiochemistry do I see for that?
Markovnikov.
Markovnikov, right? Cl goes to the most substituted carbon. H goes to the least substituted carbon. Now, the hydrogenation reaction, let me write that down here, is the easiest out of all of these. Right? It takes alkenes and turns them into alkanes. And you always have to do it in the presence of a catalyst. So your catalyst is either going to be platinum, which is seen here, transition metal catalyst, or you can do it in the presence of palladium too. Normally it's platinum oxide or palladium on carbon, right? Either one of those works. So I'm gonna write that down here, that it can be platinum or palladium. So it's a very expensive reaction to do because platinum is not cheap. All right, so what you're doing in this case is you're adding a hydrogen to both sides of that alkene. So you add a hydrogen to one side, add a hydrogen to the other side, right? So your product is going to look like this. And I'm going to put the methyl group, I'm going to keep that. Keep it facing back.
Dr. Russ, I got a question.
Come on.
You know the Mcpba rules, I think that's how you say it.
Mm-hmm.
If the product is cis, does that mean it's like that? And then if it's anti Mcpba rule, does that mean like it's trans?
No. Cis and trans refers to what we call stereochemistry or 3D orientation, right? So something that's trans or cis is going to have the two adjacent groups on the same side or opposite side. Markovnikov is dealing with which carbon gets attacked, right? So if you look at the star material, right, where you can attack here or here, each one of those carbons is susceptible to attack. So Markovnikov's rule deals with where the nucleophile ends up. It's either going to end up on the most substituted carbon or the least substituted carbon. That's why we call it regiochemistry. So Markovnikov's rule deals with regiochemistry, and then syn and anti or cis or trans deals with stereochemistry. Stereochemistry again is 3D orientation. How the bonds and the atoms are oriented in space. Does that answer your question?
Yes, thank you.
Okay. So the hydrogenation, again, I just added H2. I added hydrogen to one side, add the other hydrogen to the other side, right? Very simple reaction. And for that reaction, we've completed all those reactions. All right, any questions? I'm actually gonna stop here because I don't want to try to cram something in these last few minutes. I'd rather use that time to answer questions. And let me put the date.
Is a halogenation problem like with the halogen but then no H2O on the bottom?
Say that one more time. There's a plane flying by, so I can't. Let me turn my volume up. Can you say that one more time?
Yeah, is that like what a halogenation, like halogenation? You hear me? Hello?
Yep. So a halogenation, you asking about
Would it be like the BR2 one, but with no water?
with no water? Yes. So if you take an alkene plus a halogen, Br2, I2, Cl2, then that's a halogenation. So no water. It's done with no solvent. It's usually done neat. Well, at least that's how it's depicted in most textbooks, as being done without the presence of a solvent. I think there's one on here somewhere. And we're gonna just keep working through. Yeah, it's right there.
I have a question.
Go ahead.
So do you think, well, first of all, when is the test, and do you think we would have to draw these on the test, or?
Well, it's gonna be at least one problem on the test where you have to draw the products. I think it's one or two. I've already made the test. So the test is Friday. So it's going to be one or two of these on the exam where you have to actually draw the products, and then there's also going to be some multiple choice, true, false. I think there's a matching problem on there, and then one or two file submission problems.
Okay, thank you.
That's why we're going through this part, because hopefully you're following along and writing the products out, because that's muscle memory. The more you write it out, the more you're able to recall it when it's time to recall it. All right. Any other question about anything?
Oh, Dr. Russell.
Yes.
I never went back and checked, but I mentioned it to you last class. I think I mentioned it to you before that.
I did.
So about the,
yep.
You did?
Yeah.
You know, okay.
Yeah.
All right, thank you.
Mm-hmm. I'm surprised you didn't email me again like, hey man, did you do it? I did.
I didn't email you. I don't think I did about it. I think I just told you in class.
Yes, you did. You emailed me first.
My bad.
That's all right. I mean, hey, you got to get it how you live. So email, asking in class, however you going to do it. But yeah, I added another attempt on the post, pre, and YouTube quiz for 3A.
All right, thank you.
Yep.
Oh, when do you prefer? Well, never mind. I guess I know the answer to that one.
About?
I was gonna ask when you prefer we take the post assessment, but I guess like it'd be like right before the exam, right?
Say that again. Or for recitation?
Like when you prefer we take the post assessment.
Yeah,
module 3A.
right before you take the test.
Yeah.
Or if you want to take it this week, you can take it today. You can take it when, it doesn't matter. But no, that's just to gauge where you are before you take the test.
Gotcha.
Yep. All right. Any other questions? If not, I'm gonna get this stuff uploaded to Blackboard, get the video uploaded to YouTube, and I'm gonna send you 2 videos today to watch for Wednesday. All right. We're good?
Dr. Russell.
Yes.
For the assignments, the missing assignments, you said you wanted them all in one PDF document?
Yes.
Uploaded?
Yes.
Okay, thank you.
Uploaded to where?
To the link that you sent, the SharePoint.
Praise the Lord. I just want to make sure you put it in the right place.
Okay.
Because then you'll be on Blackboard like, I don't see nowhere to put it. Make sure you access that link too, because those OneDrive links, they expire, I think, after 2 weeks or something like that. But if it's expired, let me know so I can go in and refresh it or something, whatever I have to do. But that's due on the 31st.
Okay, thank you.
Yep.
Dr. Russell.
Mm-hmm.
A lot of the missing assignments that you put for me are like post assessments and pre-assessments, and then some of them say they were due in like 2015.
No, the dates don't. The date it's not the dates. It's the post and pre-assessments. I put that in the announcement, so you can't. It's only thing you're able to make up is the missing assignment. If you miss turning an assignment in, the post, pre-assessments, and the quizzes, that's just.
Okay, because
you can't do that. Say that.
The post assessments and the pre-assessments I've never seen before. Like they weren't in the modules or anything.
Yes, they were. every module is set up the same way, and they all have. Now, what it may be, you may be looking at something that we haven't done yet. But all
Oh,
the
it
modules
was just
had.
a zero right there, so I didn't know if that was like missing or it was something we're gonna do in the future.
No, let me look at your. Let me look at the gray book and blackboard. Do you know what specifically? You can just email me. You don't have to tell me right now. You can just email me. And tell me the specific place, and I'm gonna go and look at it.
Okay, thank you.
Mm-hmm.
Dr. Russell, this is for a chem lab question. I'm sure you've gotten emails about it. You know, the little aspirin quiz.
Yeah, I reset it Friday, and I just I put what did I do to that quiz? I changed the due date because I think I put Thursday on the quiz itself, that it was due Thursday, but something happened with the date, so I extended it to Sunday.
You don't, I mean, no, I already took it. I'm just saying like the matching on it.
Oh yeah.